The comet 3I Atlas is raising more and more questions among scientists. It's no wonder that some conspiracy theorists quite seriously claim that this is not a comet at all, but a spacecraft exploring the cosmos. In recent days, such statements no longer sound so outlandish because observations of the comet continue to puzzle astronomers. On the latest images of object 3I Atlas, taken by the Hubble Space Telescope, the interstellar comet appeared extremely unusual. It had no tail, but a clearly visible anti-tail. This phenomenon has sparked intense debate within the astronomical community and has led researchers to reconsider their understanding of cometary behavior, especially when it comes to objects that originate from beyond our solar system. The discovery of this peculiar feature has opened up new avenues of research and has prompted scientists to conduct more detailed observations using various instruments and telescopes positioned both on Earth and in orbit around our planet. Interestingly, the comet changed literally within a few days. For celestial objects, this is very unusual. In the universe, things rarely change so quickly, almost in real time. The rapid transformation of 3I Atlas has been documented by multiple observatories around the world, each capturing slightly different aspects of the phenomenon. Astronomers working at different facilities have been coordinating their efforts to ensure continuous monitoring of the object, recognizing that such dramatic changes in a comet's appearance over such a short time frame represent a rare opportunity to study cometary dynamics in unprecedented detail. The speed at which these transformations occurred has challenged conventional models of cometary evolution and has forced scientists to consider alternative explanations for what they are witnessing. Traditional theories about how comets behave as they approach or recede from the Sun simply do not account for the rapid morphological changes that have been observed in the case of 3I Atlas, leading some researchers to propose entirely new frameworks for understanding these enigmatic visitors from the depths of space. However, scientists do have a hypothesis explaining the strange behavior of 3I Atlas. According to experts, it's all due to the peculiarities of how material evaporates from the comet's surface. The process of sublimation, whereby solid material transforms directly into gas without passing through a liquid phase, is well understood in general terms, but the specific mechanisms at work in the case of 3I Atlas appear to involve several interrelated factors that create a complex dynamic system. Researchers have been analyzing the spectroscopic data collected from the comet to better understand the composition of the materials being ejected from its surface and to determine how different substances interact as they transition from solid to gaseous states. The temperature gradients across the comet's surface, combined with its rotation and the varying intensity of solar radiation it receives, all contribute to creating patterns of outgassing that are far more intricate than those observed in typical comets that have spent their entire existence within our solar system. Apparently, jets of gas escaping from the surface released grains of water ice, which, once separated from the nucleus, were more strongly heated and gradually evaporated as well. Naturally, all this happened on the illuminated side. The mechanism by which these ice grains are ejected involves complex interactions between different volatile compounds embedded within the comet's structure. As the surface heats up due to solar radiation, pockets of volatile materials beneath the surface begin to sublimate, creating pressure that eventually breaks through the outer layers, carrying with it not only gas, but also solid particles of various sizes. These particles, once liberated from the comet's gravitational grip, follow trajectories determined by their initial velocities, their masses, and the forces acting upon them, including radiation pressure from the Sun and the subtle effects of the solar wind. The water ice grains, being relatively transparent to certain wavelengths of sunlight, absorb thermal energy differently than the darker, rocky components of the comet, leading to differential heating rates that affect how quickly they sublimate once they are exposed to direct sunlight. The comet itself rotates slowly, according to estimates. It completes one full rotation in about 16 hours. This relatively leisurely rotation rate has significant implications for how heat is distributed across the comet's surface. Unlike rapidly rotating bodies that experience more uniform heating due to their quick spin, 3I Atlas has distinct regions that spend extended periods in direct sunlight followed by equally long stretches in shadow. This creates stark temperature contrasts between the illuminated and dark hemispheres, which in turn drives differential outgassing patterns. The regions exposed to sunlight heat up sufficiently to initiate the sublimation of various volatile compounds, while the shadowed areas remain frigid, preserving their volatile content for later release when they rotate into the sun's light. This day-night cycle on the comet, stretched over 16 hours, allows for the buildup and release of materials in a rhythmic pattern that contributes to the overall structure and evolution of the comet's coma and any tail-like features that develop. Observations taken at different points in the comet's rotation have revealed that the intensity and direction of material ejection vary considerably, depending on which part of the surface is currently facing the sun, confirming that rotational effects play a crucial role in shaping the comet's appearance. All of this created the anti-tail. The formation of an anti-tail is a relatively rare phenomenon in cometary astronomy, typically occurring when the geometry of the comet's orbit, the distribution of dust particles in its vicinity, and the viewing angle from Earth or from an observing spacecraft align in a particular way. In the case of 3I Atlas, the anti-tail appears to be composed primarily of larger dust particles and ice grains that were ejected from the comet at relatively low velocities. These particles follow orbital paths that are slightly different from that of the comet's nucleus, and due to their size and mass, they are less affected by radiation pressure than the finer dust that typically forms a comet's conventional tail. When viewed from certain angles, these particles appear to extend in a direction opposite to the normal tail, creating the illusion of an anti-tail. The precise geometry required for an anti-tail to be visible is quite specific, and the fact that Hubble captured this feature so clearly indicates that the observations were timed fortunately to coincide with this particular geometric configuration. Scientists analyzing the images have noted that the anti-tail appears to have a distinct structure, with variations in brightness along its length that suggest the presence of discrete clouds or streams of material rather than a uniform distribution of particles. Judging by the emissions spectrum, the comet contains a lot of carbon dioxide and water. Spectroscopic analysis is one of the most powerful tools available to astronomers for determining the composition of distant objects, as different chemical compounds absorb and emit light at characteristic wavelengths. By spreading the light from 3I Atlas into its component colors and carefully measuring the intensity at each wavelength, scientists can identify the fingerprints of various molecules present in the comet's coma. The detection of strong carbon dioxide and water signatures indicates that these two compounds are major constituents of the volatile inventory of 3I Atlas. Carbon dioxide, with its relatively low sublimation temperature, becomes active at greater distances from the sun than water ice, which requires higher temperatures to transition from solid to gas. The abundance of these two substances suggests that the comet formed in a cold environment where these volatiles could be incorporated into its structure and preserved over potentially billions of years. The specific ratios of carbon dioxide to water, as well as the presence of other trace compounds detected in smaller quantities, provide clues about the temperature and chemical conditions in the region of space where 3I Atlas originally formed, offering insights into the diversity of planetary systems and the processes that govern the formation of comets in different stellar environments. It is known that carbon dioxide begins to sublimate at much lower temperatures, meaning it was the first to evaporate from the surface. The sublimation temperature of carbon dioxide ice at the low pressures characteristic of the near vacuum of space is significantly lower than that of water ice, approximately -78 degrees Celsius for carbon dioxide compared to near 0 degrees Celsius for water under similar conditions. This means that as 3I Atlas approaches the Sun and its surface temperature gradually rises, carbon dioxide ice reaches its sublimation point first, initiating the formation of a coma and the onset of cometary activity at distances where water ice remains stable. This early activity driven by carbon dioxide sublimation can have important consequences for the subsequent evolution of the comet. The escaping carbon dioxide gas can carry with it dust particles and other materials, creating pathways and weakening the structural integrity of the surface layers. As the comet continues to approach the Sun and temperatures rise further, water ice begins to sublimate as well, often at much higher rates due to the greater abundance of water in typical cometary nuclei. The transition from carbon dioxide-dominated outgassing to water-dominated outgassing can lead to dramatic changes in the comet's appearance and activity level, and the timing and nature of this transition depend on factors such as the comet's thermal properties, the distribution of volatiles within its interior, and the specific trajectory it follows through the solar system. But there's another intriguing feature of the comet. According to data published by several independent observer groups, the object unexpectedly changed its trajectory just before disappearing behind the Sun. This observation has generated considerable excitement and puzzlement within the astronomical community because deviations from predicted orbital paths are relatively uncommon for well-observed celestial bodies, especially when those predictions are based on sophisticated models that account for gravitational influences from the Sun and major planets. The trajectory change was first noticed when observers attempting to locate the comet in the predicted position found that it was not where calculations suggested it should be. Initially, there was some concern that the discrepancy might be due to errors in the observations or in the orbital calculations, but as more data came in from different sources, it became clear that the comet had indeed deviated from its expected path. The timing of this deviation, occurring just before the comet passed behind the Sun from Earth's perspective, has made it challenging to gather continuous observational data during the critical period when the change was occurring, adding to the mystery and making it difficult to pin down the exact nature of the forces responsible for altering the comet's trajectory. The current location of the comet diverges significantly from NASA's predictions by about 15 arc-minutes, which corresponds to roughly 1.1 million kilometers, nearly 3 times the distance from Earth to the Moon. This is a substantial discrepancy by astronomical standards, particularly for an object that has been closely monitored and for which detailed orbital calculations have been performed. An error of 15 arc-minutes on the sky translates to a positional difference that cannot be easily explained by small uncertainties in the comet's mass, velocity, or the gravitational tugs from known planets. To put this in perspective, the distance from Earth to the Moon averages about 384,000 kilometers, so a displacement of 1.1 million kilometers represents a deviation that is nearly 3 times this familiar distance. Such a large deviation suggests that something significant has occurred to alter the comet's motion, whether that be an outburst of material from its surface that provided a net thrust in a particular direction, an encounter with an unknown mass concentration in space, or some other mechanism that has imparted momentum to the comet. Scientists reviewing the data have been working to rule out mundane explanations, such as observational errors or computational mistakes, and the consensus appears to be that the deviation is real and requires a physical explanation. Yet the comet's distance from the Sun remained unchanged at 2.38 astronomical units. In other words, it was at the same distance, but not where it was expected to be. This detail is particularly intriguing because it suggests that the deviation in the comet's position was not simply a matter of its orbit expanding or contracting, which would result in a change in its heliocentric distance, but rather that the comet shifted laterally or in some other direction while maintaining approximately the same distance from the Sun. Such a maneuver is difficult to account for using conventional models of cometary motion, which typically involve gradual changes in orbital parameters due to outgassing forces or gravitational perturbations. The fact that the heliocentric distance remained constant while the comet's angular position on the sky changed so dramatically implies a very specific type of force or combination of forces acting on the object. Gravitational interactions with known solar system bodies would typically result in changes to both the distance and angular position in predictable ways, so the pattern observed with 3I Atlas does not fit neatly into the standard framework. This has led researchers to explore alternative explanations, some of which involve exotic physical processes that are not commonly invoked in discussions of cometary dynamics. Enthusiasts suggest that this could only happen if the object is influenced not only by gravity but also by other forces. What forces exactly remains a mystery. The range of possible non-gravitational forces that could affect a comet's trajectory is actually quite broad, and scientists have been systematically examining each possibility to determine which, if any, could account for the observed behavior of 3I Atlas. Radiation pressure, which is the force exerted by photons of light from the Sun as they bounce off or are absorbed by the comet's surface and coma, is one well-known non-gravitational force that can influence the orbits of small solar system bodies. For very small particles, radiation pressure can be quite significant, but for a comet-sized object, the effect is generally much smaller, though still measurable over long periods. The solar wind, which is a stream of charged particles flowing outward from the Sun, can also exert forces on comets, particularly when those comets have developed substantial comas and tails that interact with the solar wind's magnetic field. These interactions can create drag forces and other effects that alter the comet's trajectory in subtle ways. However, the magnitude of the deviation observed for 3I Atlas seems difficult to explain using radiation pressure and solar wind effects alone, unless the comet experienced an unusually intense outburst or had some other special characteristic that amplified these effects beyond what would normally be expected. It could be the Sun's magnetic field, radiation pressure, or even artificial control of this mysterious celestial body. The suggestion that artificial control might be involved is, of course, highly speculative and is not taken seriously by most mainstream scientists, but it reflects the level of puzzlement that the comet's behavior has engendered among both professionals and amateur enthusiasts. The idea that an interstellar visitor might be a probe or spacecraft sent by an extraterrestrial civilization has been a recurring theme in popular culture and has occasionally been raised in more serious scientific contexts when objects with unusual properties pass through our solar system. In the case of 3I Atlas, The combination of its interstellar origin, its unusual morphological changes, and now the unexpected deviation in its trajectory has provided fodder for such speculation. However, it is important to emphasize that there is currently no evidence to support the hypothesis that 3I Atlas is anything other than a natural cometary body, and the scientific community is focused on finding explanations within the framework of known physics and chemistry. That said, the openness to considering a wide range of possibilities, even unconventional ones, is part of the scientific process, and researchers are carefully examining all available data to determine what is really going on with this fascinating object. The Sun's magnetic field extends far out into space, creating a complex structure known as the heliosphere that encompasses the entire solar system and beyond. The magnetic field lines originate in the Sun's interior and are carried outward by the solar wind, creating a dynamic environment that varies with the 11-year solar cycle and with shorter-term phenomena such as solar flares and coronal mass ejections. Comets, as they move through this magnetically active region, can interact with the field in various ways, particularly if they have developed ionized comas. The ions in the comet's coma, which are atoms or molecules that have lost or gained electrons, are charged particles that respond to magnetic fields. When these ions are swept up by the solar wind and encounter the Sun's magnetic field, they can experience forces that push them in directions perpendicular to both their motion and the field lines. While these magnetic effects are well known to influence the structure and orientation of a comet's ion tail, their potential to significantly alter the orbit of the comet's nucleus is less clear. The nucleus itself is not charged and does not directly interact with magnetic fields, but if the outgassing from the nucleus is asymmetric and influenced by magnetic effects, there could in principle be indirect consequences for the nucleus's motion. Researchers studying 3I Atlas have been considering whether unusually strong or asymmetric magnetic interactions could contribute to the observed trajectory deviation, though quantifying such effects is challenging given the many unknowns about the comet's detailed structure and activity. Radiation pressure from the Sun is another force that cannot be ignored when considering the motion of small bodies in the solar system. Photons of light carry momentum, and when they strike a surface, they transfer some of that momentum to the object, creating a force that pushes the object away from the Sun. For objects with large surface areas relative to their masses, such as thin sheets or highly porous structures, radiation pressure can be quite significant. Comets, with their irregular shapes and potentially fluffy surfaces, can experience radiation pressure forces that contribute to non-gravitational accelerations. Moreover, when a comet is actively outgassing, the escaping gas molecules also carry momentum, and the recoil from this mass loss can create a rocket-like thrust that alters the comet's orbit. This so-called outgassing force, or rocket effect, is well documented and is responsible for many of the non-gravitational perturbations observed in cometary orbits. The direction and magnitude of the outgassing force depend on where and how intensely material is being ejected from the comet's surface. If outgassing is concentrated on one side of the nucleus, or if there are jets pointing in particular directions, the net force can push the comet in a specific direction, causing measurable changes in its trajectory over time. In the case of 3I Atlas, researchers have been trying to determine whether the observed deviation could be explained by an unusually powerful or asymmetrically distributed outgassing event, perhaps triggered by the comet reaching a certain temperature threshold or by a sudden disruption of surface layers that exposed fresh, volatile, rich material. The possibility that 3I Atlas experienced a significant outburst or fragmentation event has been seriously considered by the scientific community. Comets are known to occasionally undergo sudden increases in brightness and activity known as outbursts, which are thought to be caused by the sudden exposure or destabilization of volatile materials beneath the surface. Such events can release large quantities of gas and dust in a short period, potentially producing enough thrust to measurably alter the comet's orbit. Similarly, if a comet's nucleus becomes weakened by thermal stresses, rotational forces, or structural flaws, it can fragment into multiple pieces. The fragmentation process itself would involve the objects pushing apart from each other, and if the fragments have different masses or activity levels, they could end up on diverging trajectories. Observations of 3I Atlas. Following its disappearance behind the Sun and its re-emergence will be critical for determining whether the nucleus has remained intact or whether it has broken up. If multiple fragments are detected, that would provide strong evidence that fragmentation played a role in the trajectory change. If the nucleus appears intact but shows signs of having undergone a major outburst, that would point toward outgassing as the primary mechanism. Either way, understanding what happened requires careful analysis of the available data and, ideally, additional observations to track the comet's continued evolution. The interstellar nature of 3I Atlas adds another layer of complexity to the puzzle. Unlike comets that formed in our solar system and have been shaped by billions of years of evolution within the Sun's sphere of influence, interstellar comets are visitors from other stellar systems, carrying with them information about conditions in distant regions of our galaxy. The first confirmed interstellar object, 1I Oumuamua, was detected in 2017 and caused a sensation due to its unusual elongated shape and the slight acceleration it exhibited as it receded from the Sun, an acceleration that could not be fully explained by outgassing alone given the lack of observed cometary activity. The second confirmed interstellar visitor, 2I Borisov, detected in 2019, behaved much more like a typical comet, with a clear coma and tail, and properties consistent with comets from our own solar system. Now, 3I Atlas represents the third known interstellar object, and its peculiar characteristics are adding to the growing body of knowledge about these rare visitors. Each interstellar object provides a unique opportunity to study material from other stellar systems without having to send spacecraft across the vast distances that separate stars, and the diversity among the few objects detected so far suggests that there is much we have yet to learn about the population of interstellar wanderers that must be passing through our cosmic neighborhood on a regular basis. The detection and characterization of interstellar objects is challenging because they typically move very quickly through the inner solar system, spending only a limited time close enough to the Sun to be easily observed before receding back into the depths of space. 3I Atlas was first discovered by the Atlas Survey, an automated system designed to scan the sky for near-Earth asteroids and other potentially hazardous objects. The survey's rapid cadence and wide field of view make it particularly well-suited for detecting objects with unusual orbits, including those on hyperbolic trajectories that indicate interstellar origins. Once an object is flagged as potentially interesting, follow-up observations by larger telescopes can provide more detailed information about its orbit, composition, and physical characteristics. In the case of 3I Atlas, the follow-up campaign has involved numerous observatories around the world, as well as space-based facilities like the Hubble Space Telescope, all working to gather as much data as possible during the relatively brief window when the comet is within range of our instruments. The coordination required for such campaigns is considerable, involving scheduling conflicts, weather considerations, and the need to rapidly share data among research groups so that observations can be optimized and interpreted in real time. The Hubble Space Telescope's involvement in observing 3I Atlas has been particularly valuable because of its unique capabilities. Orbiting above Earth's atmosphere, Hubble is not subject to the blurring effects of atmospheric turbulence that limit the resolution of ground-based telescopes, allowing it to capture extremely sharp images of distant objects. Additionally, Hubble's suite of instruments can observe at wavelengths ranging from ultraviolet to near-infrared, providing a comprehensive view of the comet's spectrum and enabling detailed analysis of its composition and activity. The images showing the anti-tail and the absence of a conventional tail are testament to Hubble's resolving power and sensitivity. These observations have provided critical data that will be analyzed for years to come, contributing to our understanding not only of 3I Atlas specifically, but also of cometary physics and the nature of interstellar objects more broadly. The data from Hubble, combined with observations from ground-based telescopes and other space missions, form a multifaceted data set that allows scientists to construct a detailed picture of what is happening with this enigmatic comet. As scientists continue to analyze the data and refine their models, several key questions remain unanswered. What is the exact composition of the nucleus of 3I Atlas, and how does it compare to comets from our own solar system? Are there exotic or unexpected compounds present that could shed light on the chemistry of the region where the comet formed? What caused the dramatic morphological changes observed over a period of just a few days, and are similar changes likely to occur again as the comet continues its journey? Most importantly, what physical mechanisms are responsible for the significant deviation in the comet's trajectory, and can these mechanisms be reconciled with our current understanding of cometary dynamics? Answering these questions will require not only continued observations of 3I Atlas, but also theoretical work to develop and test models that can reproduce the observed behavior. Computational simulations that incorporate outgassing, thermal evolution, structural dynamics, and gravitational and non-gravitational forces will be essential tools in this effort, allowing researchers to explore different scenarios and determine which are consistent with the data. The broader implications of understanding 3I Atlas extend beyond the specifics of this one object. Each interstellar visitor detected and studied adds to our knowledge of the diversity of small bodies in the galaxy and helps us understand the processes by which planetary systems form and evolve. Comets are thought to be remnants from the early stages of planetary system formation, preserving pristine material from the protoplanetary disk that has not been significantly altered by geological processes. By studying comets from other stellar systems, we can learn about the conditions in those systems and compare them to our own, revealing commonalities and differences that constrain theories of planet formation. Furthermore, understanding the population and properties of interstellar objects is important for assessing the potential for panspermia, the hypothesis that life or its precursors could be transported between stellar systems on comets or other bodies. While the idea remains speculative, the discovery that interstellar objects regularly pass through our solar system opens up new possibilities for the exchange of material between stars. The mystery surrounding 3I Atlas has also reignited interest in developing better detection and tracking systems for interstellar objects. Currently, most such objects are discovered by chance when they happen to pass close enough to Earth or the Sun to become bright enough for existing surveys to detect them. However, it is believed that many more interstellar objects pass through the solar system undetected, either because they are too small, too dark, or simply in the wrong part of the sky when our telescopes are looking elsewhere. Improving our ability to detect these visitors would allow us to study a larger and more representative sample, potentially revealing patterns and trends that are obscured when we can only examine a handful of objects. Proposals for next-generation sky survey telescopes, such as the Vera Rubin Observatory, include capabilities specifically designed to detect fast-moving objects with unusual orbits, and it is hoped that once these facilities come online, the rate of interstellar object discoveries will increase dramatically. With more objects to study, astronomers will be better positioned to understand the typical properties of interstellar comets and asteroids, and to identify which characteristics are unusual or anomalous. The unusual behavior of 3I Atlas has also highlighted the importance of rapid response capabilities in astronomy. When an object is discovered to be doing something unexpected, there is often only a limited window of time during which detailed observations can be made before the object moves out of range or the phenomenon in question ceases. In the case of 3I Atlas, the rapid morphological changes and the trajectory deviation occurred over a period of days to weeks, requiring astronomers to quickly mobilize resources and coordinate observations across multiple facilities. This kind of rapid response is becoming increasingly important in time domain astronomy, where the focus is on studying transient phenomena and objects that change on human timescales. Networks of automated telescopes, alert systems that notify astronomers when something interesting is detected, and flexible scheduling systems that allow telescope time to be reallocated at short notice are all part of the infrastructure needed to make rapid response observations possible. The lessons learned from the 3I Atlas campaign will inform future efforts to study similarly dynamic and unpredictable objects. Another aspect of the 3I Atlas mystery that has captured public imagination is the role of amateur astronomers and citizen scientists in monitoring the comet. While professional observatories with large telescopes and sophisticated instruments play a crucial role in obtaining high-quality data, amateur astronomers equipped with more modest equipment can also make valuable contributions, particularly when it comes to continuous monitoring and alerting the professional community to sudden changes. Several amateur astronomers have been tracking 3I Atlas and have reported observations that have helped fill gaps in the professional observing schedule. The ability of dedicated amateurs to contribute meaningfully to cutting-edge research is a testament to the democratization of astronomy made possible by advances in telescope technology and the availability of online tools for data sharing and analysis. Citizen science projects that involve the public in analyzing astronomical data have also proven valuable, allowing large volumes of data to be processed and searched for interesting features that might otherwise go unnoticed. The collaborative nature of modern astronomy, bringing together professionals and amateurs, theorists and observers, and researchers from different countries and institutions, is essential for tackling complex problems like understanding the behavior of 3I Atlas. As researchers work to solve the mysteries of 3I Atlas, they are also considering what this object can teach us about the potential hazards posed by interstellar visitors. While 3I Atlas itself poses no threat to Earth, being on a trajectory that will take it well away from our planet, the discovery of interstellar objects passing through the solar system raises questions about whether any such objects might someday collide with Earth or another planet. The speeds at which interstellar objects travel, typically tens of kilometers per second relative to the Sun, mean that any collision would be extremely energetic, potentially more so than impacts from solar system objects at similar sizes. Understanding the population and orbital characteristics of interstellar objects is therefore relevant to planetary defense efforts aimed at identifying and mitigating potential impact threats. While the probability of an interstellar impact is thought to be very low compared to the risk from near-Earth asteroids and comets native to our solar system, it is not zero, and as our ability to detect and track these objects improves, we will gain a better sense of the actual risk they pose. The question of whether 3I Atlas could be an artificial object, while highly speculative, has been addressed by some scientists who specialize in the search for extraterrestrial intelligence. The argument in favor of considering this possibility, even if only to rule it out, is that the scientific method requires us to evaluate all hypotheses that are consistent with the available data, no matter how unlikely they may seem. In the case of Oumuamua, some researchers went so far as to conduct searches for radio signals emanating from the object, reasoning that if it were an artificial probe, it might be transmitting or could be prompted to respond to signals from Earth. No such transmissions were detected, and the consensus view is that Oumuamua is a natural object, albeit one with unusual properties. Similar considerations could in principle be applied to 3I Atlas. If the trajectory deviation cannot be adequately explained by natural phenomena such as outgassing, or if other anomalies are detected that defy conventional explanation, it might be worth conducting searches for artificial signals or other signs of technology. However, it is important to emphasize that extraordinary claims require extraordinary evidence, and the bar for demonstrating that an object is artificial rather than natural is very high. In the absence of compelling evidence to the contrary, the default assumption is that 3I Atlas, like other comets, is a natural body shaped by physical and chemical processes rather than by intelligent design. The trajectory change observed in 3I Atlas invites comparisons with other instances in the history of astronomy where celestial objects have deviated from their predicted paths. One of the most famous examples is the discovery of the planet Neptune in 1846, which was predicted to exist based on perturbations in the orbit of Uranus that could not be explained by the gravitational influences of the known planets alone. By calculating where an additional planet would need to be located to account for the observed deviations, astronomers were able to point their telescopes to that region of the sky and discover Neptune, confirming the power of Newtonian mechanics and gravitational theory. In the case of comets, non-gravitational forces have been recognized as important since the 19th century, when it was noted that some comets did not follow purely gravitational orbits. The development of models to account for outgassing forces and their effect on cometary trajectories has been an ongoing effort, refined through observations of many comets over the decades. The trajectory change in 3I Atlas represents an opportunity to test and potentially improve these models, especially in the context of an interstellar comet that may have different properties than those of solar system comets. The detailed study of 3I Atlas also touches on fundamental questions about the nature of comets and the boundary between comets and asteroids. Traditionally, comets were defined as icy bodies that develop comas and tails when heated by the sun, while asteroids were rocky or metallic bodies that remain inert. However, observations over the past few decades have revealed that the distinction is not always clear-cut. Some objects classified as asteroids have been observed to exhibit cometary activity, suggesting they contain buried ice, while some cometary nuclei appear rocky and have compositions that overlap with those of asteroids. The term active asteroid has been coined to describe objects that show cometary activity but have orbital characteristics typical of asteroids. In the case of interstellar objects, the small sample size makes it difficult to establish clear categories, but the diversity already observed among 1I Oumuamua, 2I Borisov, and 3I Atlas suggests that interstellar visitors, like solar system's small bodies, come in a variety of types. Understanding this diversity and what it tells us about the formation and evolution of planetary systems is one of the exciting frontiers of planetary science. Observations of 3I Atlas have also provided an opportunity to study the interaction between the comet and the interplanetary medium in ways that are not possible with solar system comets. Because 3I Atlas is on a hyperbolic orbit and is moving through the solar system at high speed, its interaction with the solar wind and the ambient magnetic field differs from that of comets on elliptical orbits. The relative velocity between the comet and the solar wind affects the structure and dynamics of the comet's plasma tail, if one develops, and influences how effectively the solar wind can strip material from the coma. High-speed interstellar objects also spend less time at any given heliocentric distance, meaning that their thermal evolution proceeds differently than that of slower-moving objects. All of these factors contribute to making interstellar comets distinct from their solar system counterparts, and careful observations are needed to tease out the effects and understand the underlying physics. The role of computer simulations and modeling in interpreting the observations of 3I Atlas cannot be overstated. Modern astrophysics relies heavily on computational tools to simulate complex systems and predict their behavior under various assumptions. In the case of 3I Atlas, researchers have been using models of cometary nuclei to simulate how heat from the sun penetrates into the interior, how volatiles sublimate and migrate through porous structures, and how the resulting gas flows interact with the surface to erode and reshape it. These thermophysical models can be quite sophisticated, incorporating realistic material properties, detailed radiative transfer calculations, and the complex geometry of an irregularly shaped nucleus. By comparing the predictions of these models with the observed behavior of the comet, scientists can constrain parameters such as the thermal inertia, porosity, and volatile content of the nucleus. Similarly, orbital dynamic simulations that include outgassing forces can be used to explore whether plausible outgassing scenarios can reproduce the observed trajectory deviation. These simulations often involve running many different scenarios with varying parameters to identify which combinations are consistent with the data and which can be ruled out. The challenge in modeling 3I Atlas is that many of the key parameters are poorly constrained. The size and shape of the nucleus, while estimated from the brightness of the coma and assumptions about the reflectivity of the surface, are not known with high precision. The composition and distribution of volatiles within the nucleus are inferred from spectroscopic observations of the coma. But the process of inferring interior properties from observations of the material that has already been released into space involves significant uncertainties. The thermal properties of the nucleus, such as how quickly heat conducts into the interior, depend on factors like the porosity and the presence of insulating dust layers, which are difficult to measure directly. Despite these challenges, modeling efforts provide valuable insights and help guide the interpretation of observations. As more data become available and as models are refined, the uncertainties in our understanding of 3I Atlas will gradually decrease, bringing us closer to a comprehensive picture of this enigmatic object. Educational institutions and planetariums around the world have been using 3I Atlas as a teaching tool to engage students and the public with current scientific research. The story of an interstellar visitor behaving in unexpected ways captures the imagination and provides a hook for discussing a wide range of scientific topics, from orbital mechanics and spectroscopy to the scientific method and the importance of skepticism and evidence-based reasoning. Public lectures, articles in popular science magazines, and online videos have brought the story of 3I Atlas to a broad audience, helping to foster scientific literacy and enthusiasm for space exploration. The involvement of the public in science is important not only for education, but also for maintaining support for the funding of scientific research and space missions. When people understand that science is an ongoing process of discovery, with new questions constantly arising and old assumptions being challenged, they are more likely to appreciate the value of investing in the tools and infrastructure needed to continue pushing the boundaries of human knowledge. The media coverage of 3I Atlas has been a double-edged sword. On one hand, the attention has raised public awareness of interstellar objects and the scientific efforts to study them. On the other hand, sensationalized reporting that emphasizes the most speculative or exotic explanations without adequately conveying the uncertainties and the mainstream scientific view can lead to misunderstandings and the spread of misinformation. Scientists who have been interviewed about 3I Atlas have generally tried to strike a balance, acknowledging the genuine mysteries and unusual features of the comet, while emphasizing that natural explanations are far more likely than exotic or artificial ones. The challenge of communicating science to the public is one that researchers take seriously, and many have engaged with journalists and content creators to try to ensure that coverage is accurate and responsible. The rise of social media has added new dimensions to this challenge, as information, both accurate and inaccurate, can spread rapidly and reach large audiences before corrections can be issued. Nevertheless, the overall impact of the attention on 3I Atlas has been positive, generating interest and excitement about astronomy and encouraging people to look up at the night sky and ponder the mysteries of the cosmos. Looking to the future, the continued monitoring of 3I Atlas as it recedes from the Sun will provide additional data that could help resolve some of the outstanding questions. As the comet moves farther from the Sun, its activity level is expected to decrease as temperatures drop and sublimation of volatiles slows. Observations during this phase can reveal how the activity winds down and whether there are any changes in the comet's appearance or trajectory as it leaves the inner solar system. Eventually, 3I Atlas will become too faint to observe with current telescopes, and it will fade from view, continuing on its journey into interstellar space. However, the legacy of the observations made during its passage through our neighborhood will endure, contributing to the growing body of knowledge about interstellar objects and informing the strategies for studying future visitors. Each interstellar object detected adds a piece to the puzzle, and as the sample grows, patterns will emerge that will help us understand the bigger picture of how planetary systems form, evolve, and exchange material across the galaxy. The possibility of sending a spacecraft to intercept and study an interstellar object up close has been discussed for many years, but the technical challenges are formidable. Interstellar objects move very quickly, and by the time they are detected and their orbits determined, they are often already on their way out of the inner solar system. Launching a spacecraft that can catch up with such an object requires either tremendous amounts of propellant or highly advanced propulsion technologies that are not yet available. Concepts for missions to intercept interstellar objects have been proposed, including ideas for fast response missions that could be launched on short notice when a suitable target is identified, and even more speculative ideas involving pre-positioned spacecraft that could be activated to rendezvous with passing objects. While such missions remain in the realm of concept studies for now, advances in propulsion technology and the growing recognition of the scientific value of interstellar objects may eventually make such missions feasible. In the meantime, remote observations from Earth and from space-based telescopes remain our primary means of studying these fascinating visitors. In conclusion, the Comet 3I Atlas has proven to be one of the most intriguing and puzzling objects to pass through our solar system in recent years. Its unusual morphology, rapid changes, and unexpected trajectory deviation have challenged astronomers and sparked widespread interest among both scientists and the public. While many questions remain unanswered, the ongoing analysis of observational data and the development of theoretical models are gradually shedding light on the nature of this enigmatic comet. Whether the mysteries of 3I Atlas will ultimately be explained by conventional cometary physics or will require new insights into the behavior of interstellar objects remains to be seen. What is certain is that the study of 3I Atlas has already contributed significantly to our understanding of comets and has highlighted the importance of continued vigilance in monitoring the skies for new and unexpected visitors from the depths of space. As technology advances and our observational capabilities improve, we can look forward to discovering and studying many more interstellar objects, each with its own story to tell about the diverse and dynamic nature of our galaxy.